We often think space is just quiet,
Hmm.
empty, maybe. But then you hear about something like this, just, wow.
Yeah, it really changes that picture, doesn't it?
Absolutely. So back in May 2020, astronomers spotted something. They thought they saw a planet getting, well, eaten by its star.
Right. The prevailing theory then was the star ballooned up into a red giant and just swallowed it. Simple as that, or so it seemed.
The classic stellar Pac-Man scenario. But now the James Webb Space Telescope, it's looked closer.
Exactly. And the picture it's painting is, well, quite different. More dynamic, maybe more violent even.
Okay, I'm intrigued. So this is our mission for this deep dive. Unpack this new Webb evidence, figure out what really happened and what it means. Our sources here are mainly the reports on Webb's findings, like those in the Astrophysical Journal.
Sounds good. It's a great case study in how science evolves with new data.
So let's start with that initial idea from 2020.
Yeah.
The star becomes a red giant. Just remind us quickly, what does that actually involve?
Sure. So when a star like our sun gets older, it starts running low on hydrogen fuel in its core.
Okay.
It then has to switch to fusing helium, usually in a shell around that core. And this process, it causes the star's outer layers to puff up massively.
Right, they just expand outwards, hundreds of times bigger sometimes.
Exactly. And if a planet's orbit is close enough, it just gets engulfed by this expanding star. That was the original interpretation here.
Makes sense. Seems straightforward enough. But then along comes Webb, launched 2021, running since 2022. It's like the cosmic detective arriving late, but with much better tools.
That's a perfect analogy. Webb sees in infrared, so it can pierce through the dust and gas that might have hidden details before. It's giving us this post-mortem view.
Post-mortem.
Yeah.
So what did this autopsy reveal? It wasn't just a gentle engulfment.
It seems not. The evidence suggests the planet didn't just, wait passively. It looks like it actively plunged into the star.
Whoa, okay, so it didn't get swallowed,
Yeah.
it dived in.
That's the picture emerging, yeah. Less being enveloped, more like a cosmic nosedive, a death plunge.
A death plunge. Okay, that definitely sounds more dramatic. What clues did Webb find? What did it actually see?
Well, it saw the aftermath, specifically two key things. First, a lot of really hot gas, which seems to be swirling in a kind of ring around the star.
Hot gas in a ring.
And second, there's also this big, expanding cloud of much cooler dust sort of surrounding the whole scene.
A hot ring and a cool, dusty cloud. How did that add up to a death plunge instead of the red giant idea?
Good question. It's about where that material likely came from. Ryan Lau, the lead astronomer on this from NOI, our lab, he explains that the dusty, cooler stuff was probably ejected from the star itself, like the star got hit, or rather plunged into and sort of violently threw off some of its own outer layers.
So the star wasn't just expanding, it was reacting. It got, like, splashed.
Pretty much. The planet's dive seems to have triggered this expulsion. That's quite different from a star just slowly expanding and incorporating a planet into its already huge atmosphere.
Right. The violence, the ejection, that points to a sudden impact, not a slow swelling.
Exactly. The sheer energy involved seems much higher than you'd expect from just a standard red giant engulfment, especially for this particular star.
Okay, so this all happened. Where exactly? You said it was far away.
Very far. About 12,000 light years from us. It's in the constellation Aquila, the Eagle.
12,000 light years. Hard to even picture that distance. And the star itself, was it old and ready to become a red giant anyway?
Well, that's another interesting part. No, not really. It's actually a bit smaller and dimmer than our sun. Only about 70% of the sun's mass. A bit redder.
So not the kind of star you'd immediately suspect of going red giant and swallowing planets.
Not necessarily, no. Which makes the initial interpretation, while logical at the time, perhaps less certain in hindsight, and makes this Webb data even more compelling.
Right. It wasn't the obvious culprit doing the obvious thing. Okay, so what about the victim? The planet itself, what do we think it was?
The best guess is something we call a hot Jupiter.
Hot Jupiter. Okay, so big, gassy, like Jupiter.
Yep, a gas giant. But the hot part comes because it orbits incredibly close to its star. Much, much closer than Mercury orbits our sun, so it gets roasted.
A massive planet in a super tight, hot orbit.
Yeah.
And why do they lean towards that type specifically?
Well, Morgan McLeod, who co-authored the study, points out the sheer scale of the disturbance, the amount of gas and dust Webb saw. It suggests whatever plunged in had to be pretty hefty, likely maybe a few times the mass of Jupiter to cause such a reaction when it hit the star.
Wow, okay, a massive planet, tight orbit, star that wasn't necessarily supposed to be swallowing things yet. How does a planet get into that situation? How does it end up taking that plunge?
It's likely a long, slow process. We think its orbit probably decayed over maybe millions or even billions of years.
Decayed.
Gravitational interactions, mainly. Tidal forces between the star and the planet. Think of how our moon pulls on Earth's oceans.
Right, tides.
Yeah. Well, similar forces between a star and a very close planet can slowly sap the planet's orbital energy, causing it to spiral inwards, closer and closer over vast timescales.
So it was basically doomed from the start, just took a long time to play out.
In a sense, yes. McLeod describes this final stage. Eventually, the planet gets so close, it starts grazing the star's outermost atmosphere.
Just dipping its toes in, so to speak.
Kind of, but even that incredibly thin gas creates friction, like a headwind. And counterintuitively, that drag doesn't just slow it down side to side, it makes it fall inward faster. It accelerates the plunge.
Wow, so hitting the brakes actually makes it crash harder and faster.
Yeah, it's a bit like atmospheric braking for spacecraft, but obviously far more destructive. And as it goes deeper, the star's gravity and heat just rip the planet apart, stripping off its outer layers.
And that's the violence that kicks up all the gas and dust Webb saw.
Exactly. That process, the planet essentially disintegrating as it plows through the stellar material, heats everything up, expels star stuff. That creates the light flash they saw initially and leaves behind the hot gas ring and the dusty cloud that Webb detected later.
It's an incredible picture.
Yeah.
But you mentioned it's an aftermath. We didn't actually see the planet being torn apart, right? There's still gaps.
Absolutely. That's a key point. We see the effect on the star, the debris, but the planet itself, it's long gone, and we couldn't have seen the moment of destruction directly anyway.
Yeah, 12,000 light years away, happening fast.
Yeah.
Impossible.
Right. And as McLeod points out, you can't exactly run this experiment in a lab.
No kidding.
No.
So how do they reconstruct what happened? How do they get from hot gas and dust to death plunge of a hot Jupiter?
It relies heavily on computer modeling alongside the observations. Scientists use what we know about physics gravity, how gases behave under extreme conditions, star physics, and they run simulations. They can try different scenarios, different planet sizes, different impact angles, and see which simulation best matches the actual data Webb collected. It's like cosmic forensics.
Using physics to reconstruct a 12,000-year-old crime scene.
Mm-hmm.
Okay, so bringing it back home, what does this mean for us? Is Earth going to suddenly take a nosedive into the sun?
Okay, deep breaths. No, thankfully. Not like this. None of our planets are anywhere near close enough to the sun for this kind of orbital decay, death plunge. Our orbits are pretty stable for now.
Okay, good. That's a relief.
Yeah.
But our sun is going to change eventually, right? The red giant thing is still in the cards for us.
Oh, yes, definitely. In about 5 billion years or so, our sun will run out of hydrogen in its core and swell up into a red giant.
And that will be bad news for the inner planets.
Very bad news. It's expected to completely engulf Mercury and Venus and Earth. Well, it's right on the edge. Could go either way, but engulfment is a strong possibility. Maybe even Mars, depending on how big it gets.
Okay, so that fate is still potentially waiting for us, just billions of years away. But these Webb findings, do they suggest this death plunge might be, I don't know, more common than we thought for planets in general?
That's one of the really interesting implications, yeah. Ryan Law suggested this might hint that planets ending their lives by spiraling in, rather than just being passively swallowed by an expanding star, could actually be a more typical end state.
Huh. So the gravitational bands leading to a final plunge might happen more often than the star just bloating up and swallowing things whole.
It's possible. It suggests maybe these orbital decay processes are a really significant factor in how planetary systems ultimately dissolve or end. Maybe more so than we appreciated before Webb gave us this detailed look.
That's quite a shift in thinking. So the red giant scenario is real, especially for systems like ours eventually, but maybe not the only dramatic way planets meet their end, or even the most common one overall.
It could be. And again, Lau emphasizes our solar system seems fine for the foreseeable future. But this observation, it's a fantastic reminder of just how dynamic these systems are over cosmic timescales. Things change, sometimes violently.
Okay, so let's sort of pull this together. What started as maybe a simple case of stellar aging star gets old, puffs up, eats planet, has been revealed by Webb to be potentially much more active.
Right.
It looks more like a massive planet, a hot Jupiter, actively spiraled inwards due to orbital decay and then crashed into its star. A death plunge.
And that impact, that plunge, triggered the release of all the hot gas and dust that Webb could see so clearly. It's a different mechanism of destruction.
A really different mechanism.
Yep.
So the big takeaway here is Webb is giving us new perspectives on these final moments of planets, showing us it's not always just about the star's evolution, but also this long, slow, gravitational dance leading to a potentially sudden, violent end.
That sums it up perfectly. It really highlights how these powerful new tools are refining and sometimes completely changing our understanding of these huge cosmic processes.
It definitely paints a picture of the universe as much less static, much more, well, eventful, sometimes violently so. Okay, so here's something to ponder. We thought we understood how planets die, maybe swallowed by red giants. Now we see this death plunge evidence. Makes you wonder, what other cosmic events, what other processes out there that we think we have a decent handle on might turn out to be completely different or way more common once we look closer with tools like Webb? What else is happening in unexpected ways?